Hello, you're muted.
Good. Hey, good morning, everyone. This is Enno, and this is SV, let's say, last Spring Academy. Next one we're gonna meet in September. So we have it on the row already on the 16th, and today's subject is reinforcement on fixings. So you hopefully help the newcomers in, and I will continue from here. Talking about it, SV itself, then we could say that in the Nordic we are quite well established with our retail distribution. To say 1100 is quite a lot, but in other words, to say 1100 retail locations, it's a pretty good number. So from installation guys easily find us in different shops and retail areas. But maybe a good fact that SV is over 50 years on the market, 200 employees, 7 countries available. And fun fact that we're selling 5 million screws per day. So it's quite a lot of product assortment to cover and responsibility to take on quality point of view. And SV is a part of the Bergman and Beving group. From primary application areas to look at then we have carpentry, we have interior finishing, we have a building envelope area. Today a little bit touching that point also roofing, but main subject is structure. And in structural area we're looking at the timber structure or frame installation or glulam and CLT applications. So if we have today external speaker and in agenda it's just my part on the introduction, then I will hand over to Dr. Wallner Novak. Markus is since already 2013 as a guest professor in Brooks University, Oxford. He's a FHUNM professor since 2020. And his knowledge and deep so-called experiences on fire and timber structural connection. So I say just lightly, hello, Markus.
Hello. Nice to be here.
Yes, super. I can hear you too. Markus' previous subject was thermal insulation. So this is the picture we talk about it in May, and we released one sample of tool, Excel tool, which helped to calculate. Today we will bring up another Excel software, which helping you to calculate, and Markus will make a light overview on that. So we touch notch application and also such a reinforcement on support side. About SV own softwares, we making a reminder that we have SWOOD. You are welcome to register it in and look at that. What does it offer? We implement that further on, and today you will find the lateral connection and axial connection. As I introduced on the beginning myself, Enno Rahuoja, responsible on SV Timber Deck and advanced products. Experience in fostering over 25 years, and if you have any questions, feel free to send me an email or give me a call. So here are my contacts. But this is mostly it from introduction part. I'm probably not jumping into our website. If we have later on in end more time, then I will stop there. But Markus, I will handle the message or the lecture leading over to your hands. So here are some words on a picture. So I'm not going to introduce you twice as you are in second time already in our academy.
Yes. Yes. So thank you for the invitation and for the introduction also. And I want to share my screen now. and give a short overview of the today's topic. That's screws used for type of reinforcement of wood. And I have brought some general basics, and then I would like to show two examples, the notch and a support situation where we can use the screws as a very good tool to enhance the load capacities. So maybe one slide that we all know, but it's a good picture again. As we know, trees grow naturally, and they are relatively smart because they add on wherever stresses are high. So they grow as nature governs, and that's why they have a very good longitudinal tension and compression strength, but relatively weak compression perpendicular, we know, and also a very weak tension perpendicular. So in these cases, it's good to use the screws as an enhancement, so we can use the full potential of our structural elements. So that's one principle that we always have to have in mind when we use timber and construct with timber. So the idea is to, wherever there is a weak point, we imagine having a crack, and then we add screws for reinforcement to avoid this crack and to transfer the loads, like in this notch example here. And so if screws are loaded axially, they are very stiff. The development and the optimization was long going on, and it's now SW has very optimized screws for self-drilling, and also the thread geometry and everything is pretty much optimized for as low moment as possible, but as high tension capacity as possible. And so the engineer's model usually is that the realistic load transfers, the shear is interesting, how the shear is transferred from the screw to the wood is not really linear, but we assume that at half of the thread, the anchorage point is. So this is an engineering model that sometimes, if we have a look at the screws in detail, we use. It's like a little truss. So in the center point is the anchor point, and as the stiffness for transverse loading is relatively low, it's only 1/10 of the actual stiffness. We have this pendulum beam bar that we use as a model usually. And what can happen, it's also an engineering task to ask what happens before it really happens. So we think about, and then we design so that it doesn't really occur. So one thing can be that the screw is torn out completely. So the thread is withdrawn. Then we can have the head pull through. That depends on the application. It's not really important in some cases where we have two threads in two different members of wood. But sometimes if the member is not wide enough, then we have this case. So this is not always the case. And then usually it's not really governing, but we can have a tensile failure of the screw as well. And it's usually near the head, because then there we had the most shape changing parts in the production. So this is usually where if it breaks, it would break here usually somewhere. So this we know now as a basis. And then there is another thing that we have to consider sometimes. That's for the supports might be interesting. That is the buckling of the screws. So they are embedded usually in timber. And so this is quite a good situation for the buckling lengths. It's not really a high buckling problem, but we have to consider it. And that's another design that we might check, a design check that we have to use. So these are pretty much the basics in a quick run of the screws, besides the optimization of all the geometry and the tip and so on. And if we have a look at the application, number one today are the notches. So we know that whenever this is a timber is notched, relatively fast, there is this stress maximum here, this local stress that can tear or produce tension perpendicular. We saw that we have a very low tensile strength perpendicular to grain, and exactly here it's perfect to place the screw or two screws. So near support, if you have notches, then it's always good to place them from a constructive point of view, and it's mandatory and required if the notch is higher. So like this one here, the load transfer wouldn't work if there wouldn't be a screw here. And then the design idea is the same as we saw before. There's one thread length below the crack and one thread length above the crack, and whichever is smaller governs usually, and the load has to be transferred from the top to the bottom side. And from the theory and also from tests, we have a semi-empirical formula depending on the notch depth, how much force occurs in this crack theoretically, and how much has to be transferred. And that's the design provision we make. And this distance here from the support is limited with 1/3 of the height of the notched height. So the geometry range is fixed because otherwise this formula starts getting wrong. And in some cases, as the stresses are very nonlinear, we might also use inclined screws at the right side. That's a little bit more difficult to produce, and also it's sometimes better to use a cylindrical head here, as we discussed yesterday together, for the visual impact and the little damage the screw head does to the wood here. So, but still, it can be even better for the structural behavior. If the very high loads, it can improve the structural behavior because the crack stresses are very strong, very high at the starting point and then decrease rather quickly. But usually the application is this one, and the distance is kept as close to the end grain as possible. That's our main distance here. And the second application are the support reinforcements, where we add screws because we have the second weak point is the compression perpendicular to grain. We know this, that sometimes in earlier times we had some additional width glued on elements or so where the loads were very high, the supports. We tried to increase the beam width, or we had sometimes we had to or have to increase the column length or width to have a longer support. And to save wood here, it's a good option to have screws that transfer the compression into the wood by about 45-degree angle. So this is the stress distribution that's estimated, and then have so you bring in the load by the screws, and then you have a second compressive horizon here up at the tip of the screws. So you increase the load by widening this compressive area, so to speak. And then if we have a look at the engineering design check chain, So the first is that the load has to be checked without screws at the compression from the load bearing, and then we transfer the loads through the screws inside the wood, and finally we check the design at the screw tip, and whichever is smaller of these two, this one or this one, governs the design. And the screw plate here is just touching the heads, because the compressive force should be transferred equally in all screws. So that's the reason why there is a plate actually, so that the screw heads should be +/- 1 millimeter position, and then the plate helps transferring the load up. And only for position securing, that there might be a very small screw, or you could also have the column be sunken in, the plate be sunken for fire protection. Sometimes this happens, so that the position is fixed. It's just the positioning thing sometimes, but otherwise it's just a contact here. And I will show 2 examples in a few minutes, one notch and also one support where we can use also cylinder head screws here. And maybe a general, and this is a different situation. This is the end support. Then you don't have the full spread of the load up to the tip, but it's a limited one because the end grain is here. That is clear. And here is a diagram that I did once with the comparison calculation. If you have a beam with 16 centimeters width, you can increase the support load transfer by about 60%, so you get 1.6 times the capacity of a support if you use 5 or 6, in this case it was 6 screws to screw them in. And then also a provision, if we have compression and we want to transfer load into the wood, it's about 20 or 30 times the diameter to transfer the load in. If it's longer, it doesn't work anymore because the buckling of the screw governs then. So it's about, you can have in mind 30 times the diameter is about a good length for screwing compression. And then there's just one final thing about the spacing. You can look up in the ETA. It's just a hint that in the documents, in the ETA document, in the European Technical Approval, you will see that the distances are much smaller than in the Eurocode, and that helps often in designing screws and in providing a good engineering solution, because if you can pack it more dense, then it helps increasing the capacity also. So yes, this was about the theory, and to come into practice, I just want to show you the design examples we discussed and provide. I want to provide. So we have this Excel solution for the screws, and I start with the notch. And we said we want to have a beam that's 32 centimeters in height, and we do a notch that's half the height, so it's 16 centimeters. And I tested it before. We can try with 20 kilonewtons reaction force on this side, and then with this geometry, the program calculates that 13 kilonewton have to be transferred by this crack. It's not valid usually, and as an engineer we discussed this also. you think that if you consider shear and the shear part that's in the lower part has to be moved up to the upper part, the shear stress is summed up to the crack, but that's not enough because you have this non-linear crack geometry and cracking stress. So it's higher, and you see it's 13 kilonewtons, while the reaction force is 20. So it's higher than the sole shear, because then it would be 10 kilonewton if we split in the cross section to half. So it's higher than this. And then we can select a screw. We have all different geometries and variants. I stay with this one, with the cylindric head, and I also can use about 280 that we can check then if this geometry is good. The angle, as we said, usually it's 90 degrees, and timber is glulam. And the screw position we could change if we sometimes for fire reasons and sometimes for visual reasons, or if the beam is very high, we can sometimes we sink it in. We have a countersunk screw. We could set this here, and then the program calculates what's the effective length in part 1. That's the lower bit below the crack and above the crack. So we have these two lengths. We could do a little bit longer if we need, but we see that 69% is the factor. So we are safe, and we get the design capacity quite well. And the second example is the support reinforcement. I also have just enter the dimensions first. 16 by 32 centimeters glulam beam, and now we have much higher force. I go up to 150 kilonewtons. That to show what the capacity is, and we get here, if you have a look, the compressive strength without reinforcement would be 152% overstressed. So if we add screws to the support, we can enter the support length here. So if we assume that the column where the beam is positioned on is 16 by 16, then we have 16 centimeters support length, and the program then checks what the shear capacity of the cross section, and then the capacity of the support without any measures. It's over stressed. And then by using the screws, and the program calculates the minimum number. It's 5, so it looks, there's a sketch up here. Instead of 6 in this sketch, you could just use 5. That looks like a 5 on a dice. So we have 2 here, and then just 1 in the center. By using 5 screws, diameter 8 millimeters that were set up here, and 260 in length, then the capacity is reached. If the screws are shorter, the capacity will probably not be reached, because then the screws, the transfer to the tips is not enough, and we have to increase the length to about 260, 270. And if we go much longer, it doesn't pay off, because then the buckling, it goes through the beam, but the buckling then governs. So usually the length is limited at some point. Yes, so this is, I hope I didn't overstress time. This is, sorry, this let's go back to the slide here. These are the two examples in quite a quick run through, but I think that's the 20 minutes we wanted to use and give you a short overview. And it's always an engineering thing. If you have to deal with the problem, there might be some more questions, and we are ready to answer them right away if you have, and otherwise on request, Enno will be there to help you out if there are some questions, I'm sure. Yes, so this is my overview.
Thank you, Markus. Everybody, you are welcome to raise us some questions in the chat field. I see Martins have writing for us that hello, where we can find the Notch Excel sheet. Excel sheet is not yet uploaded to our website, so as soon as we have done the upload, I will send you all reminder who participate today. But if yeah, it could be and it is in the same location as I send it up that TimberTech info on 3 languages, Estonian, Latvian, and Lithuanian. We're waiting from you more questions. In the meantime, maybe I release 2 polls to you. One is related to S-Food. We are on a way to update next year also S-Food, and I'm asking maybe 2 models, what you're looking forward to be generated as addition. You found out that Notch, we are trying to support you over the Excel software, but of course the idea for the future is that you will find all in one place in S-Food. Same with the support. So feel free to give us a feedback, and you see the result in chat area. Then I will look, do we have some more questions coming in the chat field?
I have one question for Markus. It will be different if we have countersunk head for through the screw, or if we use a cylinder head for through the screw.
Yes, thank you for the question. Usually there's no difference, because in the Notch there is no difference at all, because it's the threads, the thread length that govern the design. In the support reinforcement, it might be there's also no difference in load transfer, and I think also that it's not so difficult to screw them in with this plus minus 1 millimeter tolerance for the heads. That's the only thing that is important, that you don't screw them in as you want. They should be plain, that the load transfer works. That's the only thing that's important. So in reality, there is no difference between these 2 screw heads for these applications. You don't need the yeah. And even if you incline the screws, then it's even better. If it's not a 90 degrees application, then with the countersunk heads you get this offset, and then it looks better with the cylindrical even. And also if there's a fire provision you need for the notches, for example, it's much better to use the cylindric head, because then you can screw them in and even cover them, so you can sunk them in, and that's good for fire protection also.
I have a question in chat field from Olex, and he asking, is there a theoretical background available together with the Excel for support reinforcement?
My slides.
Yes.
And there is, I mean, you have a handbook, right? That describes the things, or the most important calculations, and there is some scientific work for sure, but maybe my slides are a good intro for this. You can provide maybe
very good. I will shortly show that. I will also release another poll which is helping us to provide next academies. And please find out the two choices, what you prefer to have it most from SV Academy. Is it practical? Is it theoretical? Is it something what supports on your calculation, or is it related to fire? So please give us two choices here, what you like the most. So we can have also maybe feedback from the previous. I will say that related to additional modules, the most was asked for the whole reinforcement, 48%, and 24% was a support. Notch was 19%, and inclined was 10%. So that was a previous poll feedback. And at the moment, that poll feedback is there that the practical tips is most wanted, 47% at the moment, the situation. 18% is fire related, 6% is theoretical subject. So thank you for that. I will share my screen as well to end up the academy. We are in a close by. Who asked quickly where we can find, then I have it here as the Latvian website, but you can change here the language. If you go here on that area and choose timber, then you will find here support related to today's webinar and history, load tables, and that's the practical example. Here was the Excel from the previous, here is SWOOD, and here you can get the CAD downloads. If I click it up here from that calculation which Markus says, theoretical background, then when you go for the content page, number 5, and in the content page number 5, okay, it's uploading. It doesn't come up quick here. But here you will find out that we have that content lines, and the content lines is related to the webs, the pages. And for example, the notch is here on the page 48, and in a 40 was the support. So if you click here on 48, then you will find the theoretical background, how to calculate it. And here is the model of the calculation to get the result fulfillment. So here is practical tips and samples, and you will find a similar one for other reinforcement applications as well. But as the internet is lagging here a bit, then I'm not going to spend time here, but that's just a tip for you. To end up today's subject quick now, I think, Dia, do you see, is there any more questions arrived, or we end up and answer them by email?
There is not any more questions.
Okay.
Yeah.
But then I will do a quick end here. I thank you very much, Markus. Go ahead and look SV support tools in SWOOD promoted here, and we have also spec tool previously. In April and March introduced, so look at into the spectoolbox.com as well. So we continue in September. At the moment, the fixed date is 30th. 2 weeks ahead, we will send a reminding for all SWOOD users. So if you have been registered as SWOOD users, you will get the invitation to next academy. And here are my contacts once again to ask for technical support to find the right product or get the tips on SWOOD software calculation trainings. We have also technical expert Radoslav in Poland, and the TR voice you did her. He is also our structural engineer for Nordic region. But this is it from my side. So thank you very much, and see you after the summer. So you're welcome to give me a call if you have more questions.
Thank you.
Bye-bye.
Goodbye.